When you think about your phone or your laptop, what's really inside it? Well, the answer is billions, literally billions, of tiny little switches. And they're all made from this incredible class of materials called semiconductors. They are, without a doubt, the bedrock of our entire digital world. So in this explainer, we're going to peel back the layers and figure out exactly how they work. How do we control electricity at such a tiny scale?
Okay, so before we can really get what a semiconductor is, we have to back up a little and ask a really basic question. If you take any material, how well does it let electricity pass through it? I mean, is it like a wide-open superhighway for electrical charge? Or is it a total dead end? Or is it maybe something in between?
Wow, okay, this chart really puts things into perspective, doesn't it? So way over on one side, you've got copper. It's a fantastic conductor. We're talking a conductivity of about 10 to the power of 7 Siemens per meter. Then, on the complete opposite end of the spectrum, you have something like wood, a classic insulator. Its conductivity is way, way down at 10 to the power of negative 14. I mean, that is a gigantic difference. We're talking over 20 orders of magnitude. It's almost impossible to imagine. And then, right smack in the middle, there's our friend silicone. It's kind of meh. It's not a great conductor, but it's not a great insulator either. And that is precisely what makes it so special.
All right, so here's the game plan for how we're going to tackle this. First, we'll look at the big picture of materials. Then, we're diving deep inside pure silicon. After that, we'll meet the stars of the show, electrons and holes. And finally, we get to the really cool part, how we can actually hack the crystal using something called doping to create two very different teams, P-type and N-type.
Okay, let's kick things off with part one, a world of materials. You can basically think of every material out there as having one of three different electrical personalities. So you have your conductors, right? Things like copper. They just let charge flow like a river. Then you have insulators, glass, wood, plastic. They pretty much stop that flow completely. But then there's this third really interesting category, semiconductors. They let a little bit of charge through, but here's the magic word, the most important word of this whole thing, controllable. We can precisely tune just how much electricity flows through them. And that ability to control the flow is the secret sauce behind all of modern electronics.
So the big question is, how do we get that control? Well, to answer that, we need to zoom way, way in on the most famous semiconductor of them all, silicon. And that brings us to section 2, inside pure silicon.
All right, meet the hero of our story, a single atom of silicon. Now, what's really important here is its outermost shell. It's got these things called valence electrons. Those are the ones that get involved in bonding with other atoms. And silicon has exactly 4 of them. Not 3, not 5, 4. And trust me, that number 4 is the key to everything. Now, one silicon atom all by itself isn't much use, but when you get a whole bunch of them together, they do something amazing. They arrange themselves into this perfect repeating pattern, a crystal lattice. See, each atom uses its 4 outer electrons to link up with 4 neighbors. They share those electrons, creating these really strong, stable connections called covalent bonds. The holding hands analogy is perfect. Everyone's locked in place, making the whole structure incredibly stable. Okay, so in this perfectly stable crystal, everything is locked down. Nothing's moving, which means no electricity can flow. It's basically an insulator at this point. But of course, the real world is a bit messier than that. So let's jump into section 3 and see how we can actually get some charges, or what we call charge carriers, to start moving around.
So at any temperature above absolute zero, which is pretty much everywhere, the atoms in this crystal aren't perfectly still. They're vibrating, they're shaking around. And every once in a while, an atom gets enough of a jiggle from this heat energy that it actually knocks one of its electrons clean out of that bond. Suddenly, you've got this electron that's free. They can wander around the crystal. But, and this is just as important, it leaves behind an empty spot, a vacancy where it used to be.
And this empty spot has a name, we call it a hole. Now think about it, an electron is negative, right? So the spot it left behind now has a net positive charge. And here's where it gets really, really cool. An electron from a nearby bond can see that empty spot and just jump into it. But when it does that, it leaves a new hole where it used to be. So even though it's really the negative electrons that are hopping around, it looks exactly like the positive hole is moving through the crystal in the opposite direction. It behaves just like a real positive particle, which is why physicists have this neat term for it, a quasi-particle.
So, this is the really crucial takeaway here. In a semiconductor, you get 2 different ways for current to flow. You've got the negative free electrons zipping around, and you've got these positive holes that look like they're moving in the opposite direction. This is a huge deal,
because it's completely different from a normal conductor like copper, where it's only electrons doing all the work. Okay, so a pure silicon crystal is pretty interesting, but honestly, with just a few random electrons and holes created by heat, it's not very useful. We need way more control. And this brings us to what is probably the most important concept in all of semiconductor physics. It's called doping, or as I like to think of it, hacking the crystal.
First, let's get a couple of terms straight. A perfectly pure semiconductor, the kind we've been talking about so far, is called an intrinsic semiconductor. Simple enough. But the moment we start adding impurities to it on purpose, it becomes an extrinsic semiconductor.
And that process of deliberately adding these impurities is what we call doping. Now, I want to be really clear. This isn't some messy contamination. It's an incredibly precise, high-tech engineering process. We're talking about adding maybe just one special atom for every million silicon atoms. And that tiny, tiny change completely transforms the material's electrical properties. This is the absolute key to making everything work.
So what does doping let us do? Well, it allows us to create two completely different flavors of semiconductor, something called P-type and something called N-type. It's probably easiest to think of them as creating two different teams of charge carriers.
All right, let's make some N-type, which stands for negative type material. To do this, we sprinkle in an impurity that has 5 valence electrons, something like phosphorus. So this phosphorus atom comes in and takes the place of a silicon atom. 4 of its 5 electrons form those perfect bonds with the silicon neighbors. But wait, what about that 5th electron? It's just left over. It has no bond to hold it in place. So it becomes a free electron, ready to move around and carry current. We've basically just donated a free negative charge to the crystal.
Okay, now for P-type, or positive type. Here we do the exact opposite. We add an impurity that only has 3 valence electrons, like boron. So, when the boron atom sits in the crystal, it can only make 3 bonds with its neighbors. That means the 4th bond is missing an electron. And what do we call a spot that's missing an electron? Yep, it's a hole. So this time, we've deliberately created a surplus of these mobile positive charges. And that, right there, is the power of doping in a nutshell. We're not just sitting around waiting for random heat to create a few charge carriers anymore. No way. We can now engineer a material to have a ton of extra negative electrons or a ton of extra positive holes. We are in total, absolute control.
So let's just put them side by side to make it super clear. For P-type, we use a dopant with 3 valence electrons. This makes holes the majority carrier. There are tons of them, and leaves just a few free electrons as the minority carrier. For N-type, we use a dopant with 5 valence electrons, which means electrons the majority carrier and holes the minority. We've successfully created these two perfectly complementary materials.
And that, of course, leads us to the ultimate question. We've gone to all this trouble to create one material that's overflowing with negative electrons and another that's full of positive holes. We've built our two teams. So, what in the world happens when we stick them together? Well, the answer to that question, that's the secret behind the diode, the transistor, and literally every single microchip ever made.